Hi, my name's Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me this evening. Sorry that I couldn't get out the call to people a little bit sooner. I didn't know quite how I was going to do this, but we've got something for you. And what am I talking about? I am talking about this particular sample here, which I'm calling Hutchison effect steps. No prizes for guessing why I'm calling it that, and you'll see a little bit more of the step nature when we look at it under some strong lighting, so you can get a good idea of the form of what we are looking at here. And this is a first look at this sample. And this sample, as I understand it, was produced in the 1981 to 1983 period, the period during which he was working, John Hutchison that is, was working with his colleagues Alec Pizarro and George Hathaway. Hathaway, you might recall, is now consulting in his firm Hathaway Consulting, and they work with the Sapphire project. And so George has a long history of working on interesting things. And this particular sample, for me, when I had an opportunity to access it, was pretty special. And the reason is that I knew I'd seen it in some previous videos of John Hutchison. And I have, in the blog at Remote View, I have shared some of those. So I'm just going to start off by checking, can everyone hear me? And then if I get the go ahead, I will switch over and we'll just run through a couple of the videos that I shared on the blog, and they're queued up in theory at the correct point. So we shouldn't make too many errors here, let's hope. And I'm going to have to bounce the audio through my microphone. So sorry. Excellent. Thanks, Dan Moretti, for that confirmation there. Okay, so the first video is where John is discussing the sample and other samples that he had many years ago, and we will look at that now. So
we've had about 750 demonstrations of levitation, translational movement, metallurgical samples falling apart, changing into...
So this is the sample in question that you can see here, and he is speaking over this saying metallurgical samples falling apart. So this is a long billet of steel, and at the end, or maybe this was a division, and John said that those people who will ask questions in remoteview.icu and in YouTube, he will attempt to answer them in the coming days. So he will try to join us, but I don't know whether he can for real-time answers. But if not, he's committed himself to answering people's questions in the blog or the YouTube comments. So here he's, if I go back again, and he's saying
translational movement, metallurgical samples falling apart, changing into transmuted unknown metals, quite a variety of obscure types of effects, wood impregnated into metals.
Okay, so that is the first of the clips there, which is relevant. And thank you to John for sharing these links. He's got a photographic mind where he can find these things. I'm always impressed with the way he can do that. And you can see here that this is definitely not looking reddish and silver. And when I went to the UK and to actually Scotland to meet this collector, and he's one of a number of collectors that have offered their samples to the MFMP to look at in detail. When I went to visit him, and he had prepared the samples for me to select one to take away, and hopefully we are going to do, I have one, I look at it, and then I give it back, and this process allows me to walk through a number of samples. And he has a couple of very key samples. In fact, 3 of the samples you just saw on that video, he has But this was the one I thought I could most likely be able to get into an SEM to start off with, and I'd definitely seen it before. He was a little bit mortified because he says, oh no, I think I might have left this to corrode a bit. And I didn't quite know what he was going on about because I didn't have an image in my head of what the actual sample looked like, possibly when he received it. But maybe it looked something like this, and obviously it doesn't look like that anymore. It looks like this. And so we've got this on the microscope stage, and so I can move it around, and with this camera we can zoom in, and we'll look at that in a minute, so you'll have a good idea of what we're going, the structure of this thing. Okay, so that does not look like that anymore, but it's definitely the same sample. And in fact, he talks about the fact that it was tested by a number of people. So I think this material down here was tested by Kenneth Radford Shoulders. And I think also there is a guy called Inventor3 that has a piece of this sample. So maybe we can get access to some of the material that kind of dustified. And however, on the actual sample itself, and you can't see particularly on this image, but you might be able to on the other images, but you can on the actual sample itself. If I turn it round here, you can see there's a few areas where it's cut out here. Yeah, can you see that? And these areas here are where samples were cut for analysis, and I believe they were cut for analysis by a team in Germany. That might be the Max Planck Institute, and it might be Ken Shoulders took some samples from here. I don't know whether this was the samples that George Hathaway took, because I believe George Hathaway took some of the samples of the dustified material here. Anyway, there's a number of other little video clips that I want to share where this sample's being handled by various people. So first I'm going to go back to remote view and look at the next clip. So yeah, I guess actually on this particular image it might be clearer, the cut marks here. You see the cut marks here. So you've got one bit cut off there, and then this groove cut in there, and that is this particular piece cut off here, and this little section cut out there. So I think maybe what they were trying to do when they were cutting those sections out were to see if it was more a surface effect or it was a bulk effect. Okay, and the other thing was, well, you'll see actually in the next video George Hathaway discussing the analysis. So let me get that up for you. Okay.
In addition, when we analyzed the content, the elemental content of the pieces that crumbled off of this bar, they were very high in silicon, and yet the rest of the bar had virtually no silicon in it. Unfortunately, we weren't able to get analysis of the bar before the action of the fields took place.
So I understand that that video was recorded in 1993, and in that same video he talks about the fact that this particular sample was produced in 1981 to 1983 period. So it is a very early period sample from the collaboration and of John with other parties. And he then goes on, I don't know if you noticed there, he was talking about that there was some silicon observed in that material, and obviously you do get iron containing silicon and steel containing silicon, but he goes on to say that it was a high concentration, and we will see if we see the same thing when we look at the data we gathered on Tuesday of this week. So CSA, it's great to hear your comment there, and he's saying, I have many pieces from John, some act very strangely. I have no doubt they do. Okay, so we'll play this forward a bit, and you can obviously see there if I zoom out, that the sample on the frame there is this sample. There's no doubt about it. It is this sample. And it is a great honor to be able to have access to this sample. So if I show you that angle, and then I show you this from Hathaway's video, and this, it is definitely the same sample. So it is a great honor. So thank you to the person that provided this sample for testing. Okay, so let's go back and continue watching this video.
I also have some examples of the way the samples were mounted for XRF analysis in the electron microscope. Here's a bit of the aluminum piece that was blown apart, and these are various other samples which we've used and had mounted for elemental and structural analysis.
Okay, so he said that they conducted XRF, that's X-ray fluorescence, and this is where you hit it with an intense X-ray, it energizes it, and you get other X-rays back. And this does not give you any morphological data. It doesn't show you, it's not a scanning electron microscope. In fact, it's similar to the device that I used, but obviously a much older device that I used in Sochi in Russia when I looked at the surface of the coral twist sample. And if you remember and you go and have a look at that video, if I have the coral twist sample in here, this is an aluminium sample, and maybe I don't have it in here. I don't have it in here today. Okay. The coral twist sample had what appeared to be pits, and the pits had appeared to have transmuted elements in, and they, like one soliton, phallico-soliton ends, they seem to have the same elements in, but the bulk of the material was mostly aluminium and oxygen and so forth. So with that tool, we were able to look with an optical microscope to a certain degree, find things of interest and do samples on those. But it's not a scanning electron microscope. It doesn't really give you a morphological understanding at the fine detail. Okay, so we'll continue with George.
Please. Here is the file that you saw in the video clip before. It broke here and then subsequently broke there and there. And these pieces were magnetized so that when you put them together on a table, they would push themselves apart at the breaks, indicating a north-north, south-south, north-north magnetization, which is quite contrary to the normal occurrence. When you break a bar magnet, you get north-south, and they attract. In this case, these, what you might call apparent monopolar regions, were created and blasted the material apart.
So I have to thank Nancy Lazarian for uploading this video, because it's funny, I hadn't seen this video. I spent a long time trying to work out what Lena's doing. I actually, the study of John's materials kind of led me to believe that there had to be some sort of monopolar structures involved, and I went to talk to John about it. And he says, oh yeah, that's what George thought. Okay, so I believe that is the case, and I actually did a presentation called the Monopole Clutch, and I'll just review a couple of key points from that to address the findings or suggestions of George Hathaway there. If I can pull up that video, that presentation now. So I have it here, and in the Monopole Clutch, one of the key sequences here was this, which was the work of Oroitskiev. So I'm just going to kill my mugshot there. Leonid Oroitskiev, and he produced ball lightning, and the ball lightning produced a number of effects. It produced strange radiation tracks. It produced the ball lightning broke down into smaller ball lightning, but he also affected 57 Fe, which is a NMR isotope of iron, and depending on whether he had a south or a north part of a normal magnet on the backside of the metal that was 0.7 of a meter away from the reactor at 90 degrees for respectively north and south, they had a change in the magnetic fine structure. It actually decayed over a couple of days, so it doesn't stay, but this emission of these monopole structures stay for a period of time. And so he effectively proved, and you can read that later, that there was some magnetic charges. And if I can find the next most important slide here, this is what I mean about soliton, phallico-soliton magnetic loops. And I don't know whether I have the bit that I need in here at this point to get my context. No, I will go to a different presentation. Bear with me. I'll give you a view of the sample. There we go. And we can have some light music. Da, 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 da. Da 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 Please press 1. Okay, I've not found it there either. Okay, oh dear. What am I trying to say here? Okay, maybe. Yes. So this is a little bit more detail on the Linear-Doritzkev work, and effectively it's HHO, but we're not talking about that today. So you can see this plasmoid moving across space here, and it's got its wake. This is the strange radiation track, and this is the demonstration of the monopoles here. And it is effectively ball lightning, and other people have observed these monopole-like structures here. And here you have a situation where you have a plasma flow discharge by Bogdanovich, and it's producing ball lightning or persistent plasmoid structures. And then on X-ray film, they observe this type of it's like a mushroom cut in half, and there is a weak south and a strong north beam, and a weak south, a weak north and a strong south beam. And in this case, you've got a mixture of them because you can't control which directions they're going in. So you've got north and south coming together here with their weak fields. But over here in this experiment, they had a beamline that produced extremely high energy electrons that goes into a conversion target, like something like tungsten, and that converts it into high energy photons, in this case gamma rays, and then they have a magnet, and the magnet pulls away the electrons and just lets the gamma rays go through. And the gamma rays here have exposed the film here, but above and below you have these monopole structures. And the team at Moscow Nuclear Physics Institute that did this work showed, and they highlighted here, the fact that two are coming together back to back. And of course, this is on one pole of the magnet. So these things are magnetic, and they have a kind of pseudo-intense beam of one magnetic pole coming out of the bottom. So this is effectively like Boyd Bushman's magnetic beam structure, his patent for Lockheed Martin, of which the primer bowls are effectively an nth degree version of that awarded patent. And so what you're seeing here is the natural formation of these structures, and they're coming together because this is a north with a strong south, and this is a north with a strong south. So the north on this is attracted to the strong south, whereas in this case you could only get them coming together north to north if they were properly aligned, because it's a very, very focused, intense beam that comes out. So it's more likely the soft north and the soft south come together. Okay, so if you can imagine, so this is north south. If you can imagine, this is the kind of disordered array of generation of these structures, then this might be what's going on in John Hutchison's system. But you can imagine that the norths and norths joined together and the souths and souths joined together, and essentially what I'm saying is you get a build up of north energy and north energy in certain locations, and they have this very short fall off. But if they get bigger and bigger and bigger and bigger and bigger, they will actually rip the metal apart. And so you end up with a north and a north. And I described this a long time ago. And the interesting thing is that the work of Shishkin, which I've talked about in his... I will see if I can find that paper. Just give me a second here. I will find that video. Actually, it's a video. He talked about the different ways in which they created these pseudo-monopole-like structures, and I will get that there. And one of the ways that he created it was with gamma rays. So give me a second. And this is interesting. For what reason? Well, John Hutchison used a large sample of uranite, uranium ore, I think from the Middle East. Okay, I'll just be with you in a second. I'll go back to the presentation here so you can understand what I'm talking about. If you read this paper here, and I've got the source here, if you read this paper, the team at the Moscow Nuclear Physics Institute are saying that the gamma rays are knocking these pseudomagnetic monopole clusters off the faces of the magnet that has been used to deflect the electrons. I'll say that again. The gamma rays that coming through here are knocking these north and south beaming pseudo-monopole structures, these little sort of structures that I have a 3D representation of here. They are knocking them off the face of the magnet here. But what Shishkin found, and I will find it now, because I know what I'm thinking I should say to find it. What Shishkin found is that a gamma source itself can produce these structures. Okay, so and I want Shishkin. So this is Shishkin, and and I will get to the relevant page for you so you know what I'm talking about. So this was Shishkin's images of these particular structures, somewhere here. Okay, so this was his images of these particular structures. Okay, and it was over a 9-year period that they did this research at Dubna, north of Moscow. And it's just great that we have this information shared from them. And I will find it if I can. Okay. So here, okay, so he is saying here that they get it from gamma sources, Cobalt 60. So Cobalt 60 is a synthetic beta isotope produced in nuclear reactors from neutron irradiation of iron. And cesium-137, which is, drum roll, a fission product of uranium-235 and so forth. And so the fact that he was using uranite in his experiments would have produced these what Shishkin calls string vortex solitons, which are neutral form of exotic vacuum objects, are related to ball lightning, and they are active in producing, in my view, these monopolar structures, which it would appear that in the 1990s at least, that George Hathaway, and likely in the 1980s, because in 1986 the book E.V. A Tale of Discovery by Ken Shoulders, he talks about the fact in his conclusion of his book, which we made available, that these structures, these exotic vacuum objects, were alternating monopole structures. Okay. So there we go on that. And so essentially this is what's going on. And so if we were to do a replication, I don't know if people have been following my little videos this week. I'll go to the hold music and I have been looking at this sand here. Yeah. I'll put it on the table there so you can see it. This sand here, okay? And I've been looking with this device here, which is the radio code. And I got this radio code from another Russian distributor. Unfortunately, you can't get it at the moment. But if I show you the counts here, maybe I can do that. Just go on to the counts. Right. If I look at the counts here on this mic view over here, you can see that we're looking at 21 at the moment. And I can actually turn it on, so turn the speaker on. Let's do that. Settings on I don't need to do that. Give me a second. I'll switch back to the whole music. There we go. Okay. So I have the normal sort of counts we've got here. 0.2 microsieverts per hour. A little bit clicky there. And so I have this sample of black sand that I took from a Caroline beach, which I was told by the locals was radioactive. And it's from the highest local radioactive environment that humans normally are exposed to. And I had it for a number of years, but I had no way of testing what its activity was. And then I kind of lost it. Anyway, I found it again, and this week I've been testing it. And this is what you see when you bring it next to a something that is able to detect gamma rays, which this is able to do. So this is not detecting beta so much, it's not detecting alpha, and it's not really detecting so many X-rays, but it will detect some, I guess. And let's see what happens when I bring it close to it. I haven't heard that alarm. That's even worse than the normal alarm. Okay, so bearing in mind that this is not able to see the alpha and the beta that's coming out of this. So when we look at the spectrum here, if I go to the spectrum, we've analysed this spectrum, and you can go and see the video, but essentially this is the spectrum of the decay products of thorium and the decay products of uranium-238, and that matches the data that was shared from other groups that have analysed the sand. Now, why am I saying this? I'm saying it because if you can't get hold of a sample of uranite for your Hutchison effect experiments, you can get a hold of a sample of this. And this is able to output, in my view, these monopole structures, or interactions with magnets would be able to do it. And so you have a potential for a trigger for the Hutchison effect here. I just thought I'd put that in there. We're going to try these in various experiments. We're also going to try to remediate this with HHO technology along the lines of Mars gas technology. Okay, so I'm going to turn the alarm off here, otherwise, because it's actually capturing a sample. It really doesn't like that, does it? It goes crazy. Listen. Oh dear. It's much better with the alarm off. All your worries go away. Well, you won't even let me turn the alarm off when it's like that. That's hilarious. Okay, give me a second. I really do want the alarm off. No, it's not going to let me turn the alarm off when it's had that many pulses. That's interesting, actually. I don't want that clicking all day, so I can't. Okay, here we go. Right, put that over there, sampling. Okay, all right. So, so basically, what we showed there is that there was some breaking apart of materials. I've done a brief description of how the monopoles aggregate, and I've talked about the fact how that in the case of aluminium is only paramagnetic; it's not ferromagnetic, and so the way it binds is less secure, and it kind of moves around, and you end up with these samples which are sort of broken and fragmented. And in fact, I have a sample, I think in here, maybe it's in here, which I call fracture, and it's very classic of this manifestation of the Hutchison effect. It's like this. So if I put that on the sample table here, it looks like that, like this. And we will do more analysis of this sample at another time. So you can see how it is very, very fractured and splintered. And if you can imagine, this is a surface effect, and things go along the surface crystal grains and on the surfaces, and when the magnetic structures form, they can then get big enough to reorient, and then they, like when the music ends, as one Judy Wood said, they end up sticking back together. So there we go. It's quite a beautiful thing, really. Okay, so so that's a kind of like just a rough talk on how I understand the process to go, and one of the means of accentuating the stimulation of the process. And then we are going to just look a little bit more about what one of the people here said about it. So we will go here.
And finally, we have another set of examples. Here's a nail that broke apart and wrapped, dripped down and then dripped upon itself. Here is a screw that bent up quite sharply. And here is an example of the 1/4-inch rat tail file you saw that burnt apart and sparks flew off of it, and other various and sundry pieces. Here is a molybdenum bar that was used in, or that is used for a pin in a nuclear reactor, because it does not deform at great heat or at great temperature. And here it is, bent, somewhat like a snake. The dots were used for hardness testing, used for determining the hardness.
Okay, so he showed a sample there that looked a little bit like this sample, which I call the Hutchison effect NE sample, MFMP sample. And I've talked about that it has this triangle on this sample, and we see these triangles on various different samples. So maybe I can show you on here. Maybe you can see this triangle here, and this is a little bit like the golden ratio triangle, and we're going to talk about that with a review of some other samples later in the week. And there are a number of triangular structures over here, and I believe that those effectively are the and I'm not showing you, so that's not very helpful, is it? Here we go. You see this triangle here in the center of the frame there. This triangular structure, and it's actually like a cone, is I believe in the shape of the this triangular field beam that comes out of the bottom of the pseudo-monopole type structure. So this is this bending and twisting. And I believe that this would only occur with these intense magnetic fields. The fact that I've actually seen material disappearing in silicon dioxide with the same shape and in other materials leads me to believe that this isn't some micro machining that was done by John Hutchison. This is just a manifestation of the effect. Okay. All right, so so that's talking about the kind of the one of the signatures of the effect in my view, and I'll just talk about Colonel John B. Alexander, who wrote a book which I have down on the shelf somewhere here, called something like Unacknowledged, right? Not Unacknowledged, something like that. Anyway. He's talking here about his experience with, I believe, this particular sample. So we will go to that.
Some of the material we saw, and for instance, they showed me had a crankshaft. Remember, he's grabbing crap literally out of the junkyard, and had exposed to it. They took it to BC Hydro for testing. And the same piece of metal on one end is case hardened steel, on the other end is, soft as lead. And it just from being exposed to things. We had PVC that literally was pulverized and disappeared. Another one, they took a rat tail file, put it between two wooden boards, put it in there, it lit up just like, remember the old incandescent light bulbs, we have a wire across there, and just like that, it lights up. Got to the point the whole file, which is as big as my finger, just lit up and, broke apart. Splitting.
So I want to address the rat tail file and other examples of this glowing material. I've described it in the past, and I've described it in other videos going back some years. But just to bring it into the conversation right now, as the matter is condensing, it emits high energy photons that are able to, and beta particles, but high energy photons that are able to ionize the area the air in the immediate vicinity of the metal sample, and that causes electrons to come off or to go to higher energy levels and then drop down and emit photons. So it looks like it's red hot, or it's orange hot, or it's yellow hot, okay? But it's not. It's just what you're seeing is a surface. These particular exotic vacuum objects on the surface doing their work, and in condensing matter they are sending out photons that are ionizing the air around the sample and causing the emission of light that fools the eye into believing it's very hot. Now it does affect the material down to a certain depth, and maybe I will find the sample for I think I've got it in here actually, in here or in another one, because I cut through the coral twist sample, and that actually shows you in the coral twist sample the depth at which the effect occurs on a sample that otherwise doesn't have a lot of crystals in it, so it can't allow it to go along the crystal boundaries. So if it's able to go along the crystal boundaries, then it will do that. Okay, so here I've got the sample here. Okay, so this is the one that I was talking about earlier. Again, it is twisting, and so if you can imagine, you've got a magnet, and then another large magnet is in a different position. They want to align, it will end up by twisting the material, and of course there is a spin on magnets anyway, so you can imagine that would be the case. But I've actually got some very, very detailed microscopy images of this, but anyway, we will look at the end if we can. So in this sample you can really see that it is a surface effect. There's a lot of effect to the surface. Okay, yeah, a lot of effect, and it is these areas here which I tested in Russia and found all these different elements, but in exact ratios in the pits. You can see on the end there as well. Okay, but if we look at it on the cross section, and this is only a very small, I guess it's about, oh dear, 1/4 of an inch and to 1/3 of an inch cross section. And it took me about, I think, 30 or 40 minutes to hacksaw through with a fresh hacksaw blade. So you can imagine that if anyone's hacksawed a small cross section of aluminium like this, or aluminum for the guys across the pond, you will know that it shouldn't take that long. Well, it did. And here you can see that there are these effect. The effect doesn't go deep into the surface. Now with the fracture sample and the splinter sample that I showed you just earlier, it did go through and go along the crystal boundaries, and this was shown by Matsumoto in 1990 with his cold fusion research. And this is a nice segue to Matsumoto, because he's got some things in there that will become relevant when you see the analysis in a little while. So I'll just see if there's anything that Colonel John B. Alexander said that should be said before I move on.
The interesting piece was, this had been white hot. They reached in and picked it up, and it was cold.
That was pretty risky.
There you go. So it was cold. It was not hot. And it's because it's not a hot process. When the metal is turned to jellified, or it splits like this, or it jellifies like, or fractures like the fracture sample here, it's not doing it hot. And in fact, there's one example that John likes to talk about where Alec Pizarro, he went to go and grab a sample that had just been glowing yellow, orange, or whatever, and he found that it was not only cold to the touch, he described it as being cooler than the ambient air, that he actually left his fingerprints in it. And I've shared images of that. Thank you to John for sharing those with me. And so the fingerprint is actually in. And the interesting thing is, he was only able to push his finger into the aluminium a certain distance, not very far. And so that showed for that particular aluminium, which is not like perhaps not an extruded piece, it is a surface effect that only goes in a certain way. Okay, so I think that's probably all we need to hear from the Colonel there. So thank you to the Colonel for his comments. And if you haven't got the book, I will try and remember what the name is, or I'll get it off the shelf. Is it over here? Let me go and get that. Yeah. It's called Reality Denied. Reality Denied. Oh, there we go. And you've got, interestingly, some sort of whale disappearing into the centre of a galaxy. How interesting is that? And it has a whole section on his relationship with John, chapter 14, the Hutchison effect. Okay, it's not such a long chapter, but it does what it needs to say. Okay, so that's that. All right, so I talked about the work of Takaaki Matsumoto, and I think that this is the point at which we need to introduce this. Now, all but the last 8 pages have now been faithfully scanned and cleaned up and converted so that you can search it. So if you go to remoteview.icu, you can see that. But this is his book from 2000, which was only self-published and handed out in person to a few people. But this is Steps to the Discovery of Electronuclear Collapse. And as of probably tomorrow, the full thing will be released, and I will discuss in discussion of that when the full thing is released, but you can get everything but the last 8 pages. I will discuss this, and this shows the surface effect of how these clusters form and how they cause transmutation. And way back in his early, and this is the collapsing of material into a black hole that forms a thread of protomatter that comes out and forms on the outside, hydrogen, carbon and oxygen. And this is very important for what we're going to see later. And then in the center, you get the heavier elements like titanium and iron. So you can have what he calls electronuclear collapse. And I'll read you the preface here because it will be important to understand the premise that is made by this nuclear scientist in the 1990s. Far in the universe, nuclear collapses very often take place by the gravitational force after stars consume their fuel. Since the electromagnetic force is about 40 orders stronger than the gravitational force, it should be easy to induce similar nuclear collapses by the electromagnetic force in the laboratory. I think John probably showed that, but we never knew until now how to do that. Well, okay. Recently, the author discovered a nuclear collapse which was induced by the so-called electromagnetic force in the laboratory during studying the mechanisms of so-called cold fusion phenomena. Several kinds of nuclear reaction were directly induced by the electromagnetic force called electronuclear reaction, ENR, were found so far to occur in a special state of hydrogen clusters called itonic clusters, or micro ball lightning. The nuclear collapse was one of the most remarkable reactions among ENRs, called electronuclear collapse, ENC. Furthermore, very amazingly, completely broken materials by ENC were found to be regenerated again to thin tubes and films of conventional elements such as carbon, oxygen, and iron. The latter process was called electronuclear regeneration. And at this point, I'm just going to introduce the fact that if you go to our nuclear reaction calculator here, it's at nanosoft.co.nz. So thank you to Philip Power for working with me on the programming. Fantastic developer. And I'm going to scale into this so it's maybe a little bit easier for you to see what I'm doing. Okay. And you can do fusion reactions, fission reactions, and 2-to-2 reactions. And this is based originally on the data from the Russian Academy of Science fellow, Dr. Alexander Parkhomov. And we've extended it and built it into a useful tool that everyone can use. So if we take fusion reactions here, and we go down to put in carbon, which is 12, and we put in oxygen, which is predominantly 16, okay? And we order by MEV, which means it's going to show the elements synthesized in a fusion reaction between these two with the most energetic. That is the one that is being pushed into the smallest box because it's distorting the least space-time. And we run that query, we get answers back. And what do we get back? We get that the isotopes of carbon and the isotopes of oxygen form silicon. In fact, on this case, there's a neutrino involved. And because John's samples aren't getting so hot, so we can ignore those. So we get rid of the neutrinos. So essentially, when you try and fuse carbon and oxygen, you get silicon. Okay? And what is he saying? That when you get collapsed materials in this book, what is he saying? Maybe I can put it under the camera over here and you'll be able to see what he's saying. Let's try that. Okay. There we go. Is it going to work? Okay. He is saying, as I read, oh dear, it's changed the aspect. Let's come off that a second. Stay on aspect. Okay, all right. Give me a sec. Oh, it's upside down now. Okay. Okay. All right. Not my best work. Okay. So here, completely broken materials by electronuclear collapse were found to be regenerated again to thin tubes and films of conventional elements such as carbon, oxygen, and iron. Carbon, oxygen, and iron. Now, if you get carbon synthesized and you get oxygen synthesized, one of the next elements you can get is silicon. Silicon up here. Now, what did the analysis of the sample by XRF detect that was thought to be anomalous in the 1980s by George Hathaway? He said that there was a large amount of silicon observed. Now, there's something you should know about XRF. It's not very good at observing carbon, okay? It's good at observing things from sodium onwards. So, you know, the fact that the sodium's 23, silicon's, as you can see here, is 28, 29, and 30, they would have seen silicon, and that would have been the thing that they observed, which was out of the ordinary, okay? But we can see from here, and maybe we can't see from here because it's not actually showing it. Okay, it's not updating that camera. I might need to switch. Okay, but anyway, you could trust me. If I show you on here, maybe you can see. Furthermore, very amazingly, completely broken materials by electronuclear collapse were regenerated again to thin tubes and films of conventional elements such as carbon, oxygen, and iron. And this is called electronuclear regeneration. So, if you use this process, and Ken Shoulders talks about this, you can transmute material one way and you can transmute it back. So if you're starting with iron, you could end up by producing carbon, oxygen, and silicon, and then that fuses all the way to iron again. So you're kind of going backwards and forwards and backwards and forwards. You're driving the process. It's kind of churning the material. It's churning the material. So what would you expect to see? Well, Matsumoto and Yul Brown in the 1980s said that when he treated his material with HHO, or Brown's gas in his case, he observed the production of mostly carbon, regardless of the element that went in. And that was the conclusion that is in Matsumoto's book as well. And that is what we found. A lot of carbon gets synthesized. And I've explained why. Alpha is the most densely packing nucleus, 2 neutrons, 2 protons. And that goes off as a gas. But if it's in the cluster, then it can do something better. It can fuse to beryllium-8. But beryllium-8 decays in a few milliseconds to 2 alpha clusters. So the first thing that nature can produce, which is stable from this system, is 12 carbon. And also 12 carbon is quite resilient. So if 12 carbon gets produced and gets deposited and comes out of the cluster, or the cluster fails and so on, you end up with a lot of carbon produced. And so the claims of Brown in the 1980s, and the claims of Takaaki Matsumoto in the 1990s, and the observations we've had, point to the fact that you would expect, if John Hutchison is producing something similar to EVOs, which we know he is because EVOs came from study of John Hutchison's material by Kenneth Radford Shoulders, and Kenneth Radford Shoulders said that EVOs are the same things as ball lightning, and Takaaki Matsumoto said that itonic clusters are the same things as ball lightning, then it stands to reason that we would witness a lot of carbon on the surface. So, what are we going to be looking for? We're going to be looking for carbon and silicon in our analysis. If those things are there, it verifies what was claimed by George Hathaway in his XRF analysis, which in my understanding will not be able to see the carbon. And it's a carbon steel, so it will have some carbon in it, but you wouldn't expect a huge amount of carbon. You wouldn't expect a huge amount of carbon. Okay, so with that, I think what else do I want to say from? Oh yeah, I want to show you some images from which I published today from this book, which you can go and download, which are in the back of the book in the last but 3 papers. Of Takaaki Matsumoto. And these are relevant to what we may or may not witness on the sample when we look at the scanning electron microscopy that we did. Okay. All right. I've got to find out what's going on with this particular camera here. So maybe it's back in the room. Okay. All right. Is it? No, it's shut down over here. Give me a second. And we're going to look at this with optical microscope, which I've not done before. And we're going to look at some Narugo images that I took earlier this evening whilst you were patiently waiting for me. And we will look at some other the scanning electron microscopy and EDX, which I haven't really had much time to review. So I'm going to try and get this camera working again, so just bear with me. It's going to look a little bit mad as I flick through this thing. Where is it? Is this one, is it? No, it's meant to be this one. Okay, NDI source. It's switched. So give me a second. don't know what. I would like to have that camera, so I'm going to exit and restart here. Okay, talk amongst yourselves. I'll see if you've got any questions. I have some Hutchison samples. I made a necklace pendant out of one. This is Carissa Kinney. Great to have you here. So now everywhere I go, the Force Hutchison effect is with me. Fantastic. Yes, I believe that this will have some of these monopoles, these exotic vacuum objects in there. Ken Shoulders said they would be. I believe they would be in there. But yeah, and they would be cohering, possibly, relic neutrinos from the cosmos every time you're outside. So they may actually be energy harvesters. There might be some truth in your belief. Okay, Steve Whetstone, thank you for sharing free public information, knowledge and wisdom from excellent. No, thank you, Steve, again. Right, let me see if I can get this Talus. And see if it will actually properly broadcast the image again. Okay, all right, let's see. Is that there? Apologies for this. It's gone black. I'm still here. Don't worry. No, it really has got its knickers in a twist. Oh dear. Oh dear. Maybe. No, I think we've lost that camera for the day. That's a depressing. Maybe I can switch to the Unitech one. I want it there when we're moving around with the microscope. No. The Talus camera's just better because it has more. Okay, I'm going to give up on this in a second. Come on, give it to me. No, it's not going to do it. Let's see if it does like this. Sorry. End yet? Okay, close that. This is what happens sometimes when you're doing live things. Maybe my phone has overheated. It's possible. It is very, very hot. Oh. Okay, I'll put you back on that data for the second. Right, come on, my friend. La 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 la. No, it's still showing me rubbish. How annoying. Oh well, it served its purpose. I wanted to show you the lighting change, actually. But I'll have to publish a separate video. Is there any way I can do that? I don't know if I can do that. Okay, alright. Normal programming will resume very shortly. No, it's still showing me an image from a while back. It's obviously got its knickers in a twist. It's a shame there's no ability to... Okay, alright, that's just not going to work, is it? Okay, I've got one more thing I can try. this would kind of work, but it's distorting it. It's just not fun. Okay, sorry. Yeah, maybe it's confused because of that. Do you have any questions? What is the Hutchison effect on... Okay. Probably very good for a while. I think I came in late. Nevertheless, I will rewatch through. Very good idea. John Cliss, hi Bob, good to see you again after the conference in the Netherlands pre-COVID. Yes, that was great. I look forward to seeing you at some point in the future. Yeah, right, yeah. Let's see what we can do. No, it's just not going to do it. Interesting. All right, so obviously the software here has got a bit confused. So we have lost that camera. So I don't know whether I can do what I wanted to do on here. Maybe I can do it just quickly on my camera here. Okay, all right. So what I wanted to do actually was to on that other camera, which is rather lovely, but it is what it is, isn't it? Not everything will work all the time when you want it to. But I will share a separate video with what I'm going to try and get across here in a second. But I have a very bright little light here. Very bright. And I wanted to show the fact that, you know, this, why I'm calling this the steps. So this may or may not give you an idea of the morphology of what we're looking at here, or the bulk structure. This would have been much better on the other camera, you can imagine that. Okay, so there are the steps, and I think that probably is showing something about what happened to this sample when it tore apart from the bulk of the material, or the bits came off it. The reason they came off it, there was some organized structure going on here. Anyway, sorry that's not what I wanted to show in the way that I wanted to show it, but can't always have everything we want, can we? That's just such a shame. That is not. Maybe it's got some sort of buffer, and if I reset, I'll reset my phone. Anyway, it probably will. Okay. Oh my god, so boring. Dear. Right. These funny phones, you have to do something really odd to turn them off. Restart, my friend, restart. Maybe you can sort it out after that. So, we were talking about the fact that electronuclear collapse, which is caused by ball lightning or itonic clusters or exotic vacuum objects, whatever you like to call them, will lead to the production of completely collapsed materials, and that will lead to them regenerating, and one of the first things that they regenerate to are carbon and oxygen. If you know your elements of the Earth's crust, oxygen is the single highest concentration element in the Earth's crust, and it is, drumroll, silicon that is the second highest element in the Earth's crust. And just for confirmation there, this follows my phenomenological hypothesis. So there you go. Oxygen here is 4.61 times 10 to the 5 milligrams per litre in the Earth's crust, and silicon comes in at second at, you know, getting on for half of the amount there, or 40% or whatever, and then aluminium comes in next, but then iron comes in here. So the fact that you could have carbon produced and then oxygen, and then that rapidly goes to silicon, and then that rapidly goes to iron, and you're starting with iron, then it's unsurprising that there is some regeneration and reproduction through the regeneration in this process. So there you have it. So there's a couple of images that I wanted to share from Takaaki Matsumoto from the parts of the book that I have made available today. Okay, so I'm going to go into Photoshop now. Right. So here you can see a sphere of lead, I think this is, and these are the hollow spheres that get produced, and they have a pole and from that pole you end up sometimes material being emerging. Sometimes you get two at the sort of this sort of right angled structure, and sometimes it's a little bit more intense. And from the pole here, there's another hole here, so this is your kind of right angled thing going on here. But anyway, from this hole you have here, you have a plume of carbon coming out. And in fact, one of his most extreme ones was this one here. And you can see this is a lead ball down here, and this is carbon coming out. And in this experiment, he had potassium hydroxide, hydrogen, oxygen dihydride, which is like water, and he had what do you call it? Lead wire. So there was no carbon in this experiment. He was producing HHO, and it was producing these balls, and out of this structure came this. Now, he's essentially saying that these hollow structures end up, something goes on inside them, some fields are causing these spheres to occur, and from the inside of this, out comes this material. Now, we've observed this in our work in Vega experiments with Henck's exposure with plasma in a low-pressure air environment, which obviously will have some water in there, so you've got a bit of HHO in there. And we saw these spherical holes with carbon structure to them. So that's that, but also in the 1992 patent of what's his name, Solin, he talked about the fact that the material, the transmutation, occurs in hollow spheres and tubes. Hollow spheres and tubes. And I don't know whether it says it in this particular recounting of no, I don't think I've got it in this particular segment of his work. Do I have it in this one? In the Solin patent here. So this is the Solin patent, and he was doing electron beam, you can see here, into a low vapor pressure metal, and this produced these structures, and there was nucleation of magnetically charged particles in it. So this was particles that were effectively monopole-like in nature. Magnetic charges that automatically arise and are maintained in its volume lead to the decay of protons. This would be collapse of matter and are catalysts for nuclear reactions. With increasing concentration of magnetic charges in the active medium, the intensity of the course of nuclear reactions increases spasmodically. This is achieved by creating conditions for self-compression of the mass of superconducting nuclear condensate. Due to the formation of mobile active centers domains in the active medium, they have the form of hollow spheres and cylinders. Hollow spheres and cylinders. This is very important when we're going to look at the Hutchison steps sample, as I'm calling it for purpose of reference. Inside them, nuclear fusion reactions occur. Magnetically contaminated particles are generated and accumulate with the generation of superconducting currents. Electromagnetic, nuclear, and gravitational forces are combined with the formation of coherent radiation. Okay? Active centers whose shells are composed of superconducting nuclear condensate rotate. They have a magnetic and gravitational field. Thus, active centers act as gravimagnetic rotators in local zones. In the areas of their accumulation in the active medium, superconducting current, eddy currents, and circular waves with white glow, pulsations, and local explosions, orderly directed self-accelerating mass flows in the form of cone and cylinder arise. We've observed this. John Hutchison observed this, John Hutchison observed this, we've observed this, and he's talking electronuclear collapse. Active centers interacting with each other move and join, jellification, joining together would end up with larger active magnetic structures and then increase in their size. This process has a self-regulating and resonant character. So if it's resonant character and you drive it with frequencies, then you are going to be able to get this to get bigger and bigger and bigger. Under such conditions, nuclear transformations spontaneously activate, propagating from the central zones of a liquid bath to its peripheral regions. Liquid, molten, I don't know, is it melting point? Is it really liquid? Is it really molten? Ultimately, the conditions of explosive compression of the active medium and the operation of a quantum nuclear reactor with maximum energy intensity are achieved. Large domains, diameter of 40 to 50 millimeters, in this case, are carried out by the shock wave onto the free surface of the active medium and collapse. This process is accompanied by the summation of superconducting currents and the coherent radiation flux generated in local zones. Protrusions and depressions. Protrusions and depressions. Could this be like a yin and a yang? Could this be like a peak and a trough? Periodically occurring on its surface correspond to the maxima and minima of the intensity of the spontaneously generated alternating magnetic field and characterize the appearance of magnetic solitons of two different polarities that are magnetic. What is a polarity that is magnetic? Oh, could that be a monopole? In the resulting magnetic superconducting liquid, like we have seen in the Vega Valley that produces this structure behind. The physical processes in this substance are similar to those that occur in superfluid, superconducting nuclear plasma neutron stars. And what does Matsumoto have in his book, in this diagram? He is saying here multiple neutrons lead to tiny black holes, and effectively you get electronuclear collapse through the self-compression of matter. But that was in the mid-1990s, 1994, I think 1995, and Solin submitted this patent in December 1992, having completed a long period of research. Therefore, it is detected spontaneously without chemical etching or nuclear fusion product, fusion product. Due to the implementation of a coherent ultra-fast explosive crystallization, it consists of many fragments and dispersed areas in the form of ordered clusters of microcrystals, which are separated from each other by voids. And so this is some structures that you will observe potentially in a sample that has undergone this type of process. What I am saying is that Solin is talking about soliton-type structures. These are forming magnetic charges. They can aggregate and form larger clusters, and the larger clusters can get to the point of collapsing. But in somewhere in the middle of there, they form hollow structures in the form of spheres and tubes, and this is where the nuclear reactions occurs. We've observed this, and in fact, when I was in Sochi in 2018, I sat next to Klimov, Anatoly Klimov, who is one of the leaders of the All-Russian Plasma Physics Institute in Moscow. And he said, what we're finding in our experiments, and he's using a Tesla coil and a plasma in a vortex, having gone and worked with Ken Shoulders. This was the device that they came up with, having worked with Ken Shoulders, right? Ken Shoulders, having learnt and used his skills, building off what he observed with John Hutchison. What has been said was he sat next to me in breakfast after the Sochi conference. He was talking to another Russian scientist. He says, what we find in our materials are these hollow spheres, which have kind of like micron scale thick thicknesses. He observed it. We've observed it. Matsumoto observed it. We've observed it with the Vega experiment. Will we observe something similar? Maybe, I don't know, in the analysis that we will look at today of John Hutchison's sample. So, hi Slobodan. So we haven't actually shown the data yet, so it's great to have you with us. So basically, I've gone through how you stimulate the effect. Obviously, there's a fixed electrostatic field, either from a Van de Graaff generator or from a Tesla device. It just needs to be, it's directing that what you need to direct. there's magnetic fields in there, and the magnets may be important. There are gamma sources, and I've shown how those can stimulate the production of these magnetic solitons. And then it's shown to be a resonant phenomena that can cause clustering, and that it leads to the production of spheres, toroids, and tubes that, in my view, from the Vega Valley here, you can have a ball lightning here and a ball lightning here, and it wets together. It wets together. And that leads to the production of a tube. Yeah, it leads to the production of a tube. Okay, so if you had a pole at this end, it would then might spray out material. Okay, so these electron condensates can wet together, and they form these zones which are counter-rotating. And in there, you can go back to the early Maxwell papers, and he shows, and I will talk about this, how it forms this hexagonal lattice, but it's not quite like that. From my studies, it actually forms like buckyballs. All of the allotropes of carbon, they can then mesh together into tubes and stuff. So go and look up at what structures carbon can form, but typically it's hexagons and pentagons that can arrange and form tubes and capped tubes and planes and spheres and so on. And so it basically can do all those structures. And in there you have these superfluid, fluidized electrons which form these magnetic charged zones that then can aggregate and lead to the collapse of matter. Okay, so I think we're going to look under the optical microscope because we've lost one of our cameras. Maybe it'll work again. I'll try one last attempt to get this. Now I've rebooted the phone. So maybe I can get this to send an image again of some use. Talus. Okay. All right. It's just much better with that one. And that's probably a no. It's still showing rubbish. One last attempt to get this working. Come on, my friend. Give me the image. No, it's just going to refuse to do it. No, it's going to refuse to do it. Okay. I tried, and I tried again. All right. We'll move on to our optical microscope here, which I'm showing you an image here, but it's not actually showing anything useful because I'm not looking at the sample yet. So we will look at the sample. And I'll move it over. And so there we go. Right, lovely. And I need to move this onto a different screen so I can see what I'm doing. And move that over there. And okay, all right. Can you see where it is yet? All right, it's still showing that rubbish thing up there, so we get rid of that. Okay, all right. Alright, so this is the Dynalite Edge software, and I'm going to move the camera around here. Is it? Oh no, is that gone as well? Oh no, it's lost all my feeds. Oh dear. Let me kill that camera. Oh no. At least this does reset the camera. Yes, it's reset the camera. Okay, so it's not the end of the world. Okay. Okay. All right. Ooh, are we there yet? So I'm going to go up to the kind of area that we were looking at under the SEM, which is kind of over here. Maybe it's a little bit high, it's on the wrong place. I'm just moving up and down on the sample here. Right, and if it's remembered what I asked it to do earlier, it should. No, it's not done it. Settings, micro touch, start automate. Start. Okay, is it going to remember that? Now, I'm sorry about the flickering here. It's going through a hub, and the hub has other things going through it, and for some reason, it just dims the image. It's just a bit odd. It does that. But it does that from time to time. Okay, so it's doing its focusing there. So we should be able to focus up and down. And you can see these kind of like, this is a kind of hex. I'm looking at this for the first time. So this is real time for me and for you. So yeah, you can see this kind of hexagonal section here and this wave and a wave and a wave. So this is overlaying that, it's overlaying that, overlaying that. Well, I'm just looking at this for the first time. So don't expect me to know what I'm looking at. Okay, we should be able to change our focal point here. Sorry, that's really annoying with the flickering. It's annoying me. Now, what did Solin say? You have these up and downies. Now, as I showed you earlier, this looks a bit rusty. It does actually look a little bit rusty, and this is unfortunate. But you know, life is what it is. It should have looked like this. Yeah, it should have looked like that, but it doesn't. It looks like this. Okay. And in fact, my picture that I took on the day is the title frame for this video, and that is that. So you can see that that does not look like it hasn't had a little bit of rust, and you can see some of the rust on the side here. So we will expect some additional oxygen confusing our analysis here, and it will have captured that from the air. The hydrogen we can't detect anyway with EDX. Okay, but as I'm looking at this now, I don't know whether you think you can see it, but I can see a kind of like section here with the spot in the middle. So I don't know, I'm going to rotate the lights here. That's all the lights. Yeah, there's definitely a spot in the middle and there's structure around the outside. Now, where have I seen this before? Where have I seen this before? Possibly I've seen this in the work of Matsumoto. Not just once, but many times. Okay, so let's have a look at this. These are the ring spots. There we go, ring spots. And we've seen this on other Hutchison samples, like the fracture sample. So here we go. We have the ring with a spot. And these are kind of the hexagonal structure. So already I'm becoming convinced in my first few seconds of looking at this that this is demonstrating the same process that occurs. And you have an innie and an outie, and one is one pole and the other one is the other pole of the structure. So I'm going to change the lighting. I'm going to make it brighter, but I'm going to turn off. So this is one angle, and I'm going to change. You can't see actually, the screen grab doesn't pick up the things that I'm changing here. It just shows you the underlying image, which is a shame, but anyway. So I'm going to look at this angle, look at this angle, and this angle. I'll turn those back on, bring the light down a bit. Yeah, so it's this kind of structure here, this hexagonal structure here with the spot in the center. There's another kind of hexagonal here. It's not so clear. It's a shame that this material has got some corrosion on it, but it is what it is. Right, let's see if you can see. Focus into that differently. And I'm going to change the specularity. I'm going to move back to that one. What I've done is I've just changed the specularity. I actually can't see you guys at what you're commenting, so let me bring your panel down the bottom here so I can see you. That'll be helpful to me. Let me go here and bring you down, and I can actually know if there's anything you want to ask. tetrahedral arrangement graphite. Yes, it's, well, actually, it's yeah, kind of graphite, but no, it's the hexagonals and the pentagons mostly. Okay, so I'm going to move around here. I've got the spectra. Okay, all right. I have no idea what we're going to see here. Okay, so I'm gonna go back to that image and grab that area there and just grab that structure, because that we've seen that in many different kind of. It's not the best example, but we've seen it in many different systems. Okay, see if it's better with the. Okay, all right. I'm going to mumble to myself a bit here as we go around the sample. Okay, so you can. This actually has a hexagon in it, and it's kind of like on its own. It's quite interesting. I don't know. I can't zoom into that anymore. Maybe I can. There's a magnifier function, but anyway. So I'm looking at the most raised area here of the sample. So this is the one that was most prone to damage over its life, and it's quite a long life. It's from possibly as old as 1981, so this could be 40 years old. I'm on, yes, the top step of the steps. That's where I am, Victor. So, oh, this is lovely. Look at this. So, you've got the hexagon structure here with the spot in the center. 100%, I can pretty 100% say that this was done with the same family of technologies, and it's related to ball lightning. So what we are looking at here is definitely a sample that was exposed to the Hutchison effect, in my opinion. And this is based on systems that I've looked at that have been under ultrasonics, been under plasmas. At some point in the future, there'll be a whole group of people that'll know exactly what they're looking at. Always. I'll know, oh, I know what did this effect. I should have taken a picture of that one back there. It was lovely. Where is it? Down over here, is it? I'm moving the focus point around. Is it that one? Maybe. It's not such. Yeah, maybe there. So you've got this particular angle. When you see this, it's with the spot in the center. So the center is there. There's the spot. Can you see my mouse moving? Yes, you can see my mouse moving, man. I'm not talking to myself. So we'll take that. Okay. I wonder if Ken Shoulders had the ability to look at the sample like this, or did he just have a small section of the sample? In some respects, the fact that this has corroded, you know, like you see the section here, it's not the best example with the spot in the middle. It might help us define the structure. So I might have to do a much bigger survey of this and stitch it all together without the flickering going on. Oh dear. Yeah, so I'm on the top plateau, and this is some of the area that we will look at under the SEM. And you have to look at samples with different technologies. Just if you look with one type of technology, you are likely to misinterpret things. And partly the reason is, for instance, in this technology, you've got a ring light that's made of 8 LEDs, and they produce their own artifacts on the surface of the sample, and you might end up interpreting things wrongly. So if I turn these LEDs off, you can see the form. This is interesting. This is probably one of our ring spots here. That's on my wedding ring. Here we have ring spots. That's how confident I was about this technology. I was willing to put it on our wedding rings. So, yeah, I might be a fool, but I'm a fool with a reason. Okay, so, yeah, you see, for instance, if you're not lighting from that particular angle, because it's in shadow, you can't actually see the form of this pit down here. It ends up not being revealed. So, okay, so what's the best couple of ones? Maybe that one. Okay. Now, with a lot more effort, you can get more depth of field. So I'm actually changing the focus here. This plane. Okay, so there's kind of, and it's interesting. Here you've got two of these things. You've got a cluster of three actually there, 1, 2, 3, and with the spots in the center. And this one's a bigger one, but the rust is all around it. This hasn't got so much rust on it. And this would lead me to believe that this has a different proportion of elements in it. And in fact, in Matsumoto's book, he actually shows these hexagonal structures with a map of elements that are synthesized in there. And absolutely, they are a different proportion of elements in there. In the book itself that I have here, it is in black and white. But in the book that you will have, it's in much higher fidelity. And it is in color. So I'm going to show you what I'm talking about here. So maybe you can see this. So like I say, it's not great quality here. This is a pentagon structure, and there's a hexagon structure. There's another hexagon structure here. And on this page, which we have this in color, and in fact I might put this on the back of the printed version. You can see maybe the hexagon structure here, and they've got different levels of sodium, potassium, cadmium, iron, and chlorine, and he's got this colored, and so it's very, very different from the background area here. So probably what's going on in this image we see here is this kind of thing, where the magnetic charges, which probably caused this material to split apart, synthesize different elements and led it to be brittle and fall apart. So I'm getting a lot more than I actually expected from what I'm looking at right now. I did not expect to see this much. So there's one actually. Okay, there's a chain here. It's not maybe so clear to you. Maybe I can change the lighting or change the polarization. Is it clear on different polarization? So there appears to be a chain here. There's one with the ring, with the spot in the center. And maybe if I change the lighting on this, I can determine whether it's a peak or a trough. I'm not entirely sure, but I think it's a peak. Okay, so we looks like we have a chain there. We have one down here, one here. This might be a trough. This looks like a trough. This looks like a peak. So maybe these two are a half soliton pair. And so you can imagine that if there was flux, magnetic flux going between here and here. Are you looking at me? Sorry, you're looking at me. Sorry. I'm looking at this structure here. So this is a peak here, and this is a trough. This is the opposite magnetic charges referred to by Solin, peak and trough. So you've got a dimple here, and you've got a raised bit here with a roughly hexagonal thing. And the distance between the outside of this and the center there. So actually, I'm going to measure this. Why not? Let's measure it. So from the center of this structure to the outside, this is 150 micron radii, roughly. We'll move that over. Ooh, no, come on. I don't know whether flickering is as bad for you as it is for me. So That is our peak from the center out. And I'll measure the center from this one out. I'm glad this is actually coming through. So, oh dear, the focusing is gone now. Oh no, let me do it here. And it's completely lost the position. Oh, thank you. Oh dear, come on, you can do better than that. Okay, I've completely lost the position and it's losing it on the oh dear. Slightly easier when you're not having to use several computers and moving between them. I don't want to lose that particular sample, so it's going to let me focus. It's going to let me focus. I might go to the focus limit here. Okay, I've gone to the focus limit here. Okay, there's the structures. I'm going to move them better into the center of the frame. We'll try and measure them again. This is incredibly exciting to me. I mean, I can't imagine. I don't know what you guys feel, but for me, this is amazing. It's just truly amazing to, after 40 years, be able to see these structures on this sample. So thank you to the Scottish collector for sharing this with me. But 100% certain this is not anything fake. What happened with this, in my view, is the same thing that happened in many of the experiments that we've conducted. So the trough is, they're in the same magnitude, very, very closely. So the peak, the trough here, roughly, it goes up and down. If I change my focal position, it'll change. Yeah, this is just awesome, just awesome. The volume is low. Is that? Can you hear me now? My volume is low. I don't know. Okay, so yes, it is the comma shape. So one is the yin, one is the yang, and I'll come to this. But I believe that the structures that form the iron crenellated spheres are effectively the maker, and the breaker is the one that forms the carbon and so forth. So, and they're the ones that you still see the carbon coming out of the center section. So it's the circular section in the center that sorry, it'll actually be this one, I guess. The material's coming out of that, and it's from a spherical structure, but in this case it's two toroidal structures that do this work. But there we go. So we're of the order of about 150, 152 or something microns across for these polar structures. And I will hide these two measurement points. And yes, I've got those measurement points recorded. Okay. So, I mean, this is just, oh no, what's happening now? Oh dear, it's lost the camera again. So, let's do what's going on. Okay, and come back. I don't know if everyone's familiar with the rest of the work that I've been doing that has shown that these are the signature things, the signature structures. But you can go and look at my analysis of, for instance, the... I've got that too far away now. Ah, hold on. I'll change the zoom on this a bit. Okay. Take those off. Right. Okay, we're on a different area here. Can I focus this way? Yes. Oh, look, I mean, there you go. The edge outline. Oh, oh dear. You can even see on the edge here, you've got this glunk, glunk, glunk. when I don't have it putting through the stream software, you don't get these blinking. So I just apologise to everyone for the blinking. It's because I'm going through a hub. I wonder if I can avoid that. No, I can't avoid it today. Not can't. So we've got a trough here and we've got a peak here. So I think we're going to see this same kind of pattern repeated. What I will try and do is if I can get on the SEM again. Actually, the SEM that I looked at this on, I was actually on trial. And I'm hoping to find sponsorship to get it. I've got quarter of the money already raised on the, you know, to try and get it. And then it will be a case of not borrowing and seeing if I can get access. I'll be able to do proper long-term studies of things. Because I have literally probably hundreds of samples now that need to have some love and attention from different experiments. Okay, look, I mean, look at that pit there. You see the hexagonal structure? Okay, so you've got this one down here with the pit in the center. I don't know, it's not so clear. I'll take a shot of that anyway. You got a pentagonal one down here. Oh, a lot of disruption over here. There's a lot of action here. Oh dear. A lot of glassiness as well. So there was probably this is an area where there was a lot more silicon generated. Or it might just be metallic iron. Very shiny, but not able to rust because of what's going on. So you can see these highlights here, which are because of the LEDs. See the center point here, the center point here. This was so I think I'm now looking at the second step down. If I had the other camera working, you would be able to monitor where I am. And it's heavily disrupted here. And I actually prefer areas that are not too disrupted, because you can actually see, so there's a hexagon here, there's a different size here, different one here. And I mean, you can actually see craters on craters. Let's put it like that. There's a bigger structure here, and then there's a smaller one here. So it becomes messy when you get too much going on. Yeah, it's just too much to going on there. So I'll maybe go to, where are we? Let's see down here. And I'll take some images with the Sony because it produces images where it captures at least as high a resolution as this Dynalite does. It's a little bit more hard work, but the fidelity is fantastic. Every pixel's a winner. So even in this very flat area, I don't know if you can see it, whether it's coming through on YouTube, but there's a pair down here. Oh dear, this flickering is so tedious. Devices that are not designed to go through a hub. Right, I'm going to look at the third level down, which is I'm going to need to adjust the height of the microscope here. It's going to let me do that. Yes, it's going to let me do that. Okay, all right. So I'm on the third down, and you can see the spot here, Not the best example. Okay, so you can clearly, this is interesting because it's almost like a cut plane. You've got the hexagon structure here, so maybe I can do a section across, oh no, is that working? Like there, and then we got, oh, come on, stay in focus for me. Oh. Oh dear. And then we got the last plane here. Okay, in this last angle there, it's the last cross section. I'm not quite centered on this one, am I? That one should be there. In the center. This one should be some of these things you have perspective on, that distorts things. So, but this looks like whatever happened here got overlaid by some action that happened on top and kind of ruined it. So. And there might be some perspective going on there, so I'll take those off. Okay. Move this way a bit. Okay, so I'm going to go on to the SEM. I think you get the general idea. I think this has had the ring spots, the magnetic charges on there. I would conclude that my inference, supported by the prior claims of George Hathaway and the discovery of Solin and Matsumoto, support the fact that this is ball lightning. And it does the same thing all the time. And just John is creating it in a very, very novel way by using fields. So let's see what we see when we look at this under the microscope. Okay. I actually took some pictures earlier as well, real pictures. So we are going to lose that and go back to my mugshot. Hello. Let me see if I go into here. Give me a second. La la la. So I actually took some images here using the Narugo. So you'll see it in a second. There's a lot of images of the same thing. Yeah. Can you see that? And you can see there's a layer on a layer on a layer on a layer on a layer. So, you know, I thought that was quite interesting, that particular shot. They've got a different look to these. So maybe here you can see one of these ring spots, and that's a six-sided ring spot there. Okay, so I'm going to use this technique because it gives a different fidelity in how we look at these things optically. And this is looking at that structure again from a different angle. Some pitting going on. I've got some video here, have I? Let's see. Yeah, I'll share these videos and images on remote view at another time. So yeah, this ring spot here. There's another one here. So this is maybe an innie and an outie. Don't know whether I've captured that very well. No worries, Slobodan. Sorry, I wanted to get to the SEM images sooner, but we're nearly there. Yes, it is worth looking at the rise, but I think the rise tends to be where it's torn away by the magnetic fields. But I will have a look at the rise, Victor. So it's very, very disrupted looking at this. And we're back to where we started. Okay, so let's have a look at the SEMs. Why not? Second flow blah 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 blah. Okay, right, and I'll move those in. Okay. Right, so there isn't that many SEM images, I'm sorry, but that's just the way it is. However, we have some SEM and it's a start. Okay, so the first image here, they are relatively high res. You can see some cut through here, and this looks metallic and so forth. Maybe we have a kind of disrupted area down here. I don't know. Maybe we have a cardioid type structure here. Don't know. This is where you need a lot more work done. And the question I have with this is, are these just rust structures? Or is there something more interesting going on? Was this area here cut out? Was it cut out? Are we seeing a vortex pair, this hexagon and this one overlaid, just like you saw with Matsumoto and we've explored with ultra experiments? I don't know. Is this a hollow structure? don't know. But what I did see was these structures on here. And so I zoomed into that, and I zoomed into it some more. Sorry, here. And I'm seeing these things, and they are like, I don't know, I suspect that they are created by this technology. But when I look at them, I see something that may be pollen, or it may be mushroom spores. I don't know. But similarly, it has these points all over it with these spikes coming off. And we've seen this in the Vega Valley, but not in these discrete structures. Now, I will show you some things that we have seen in the Vega Valley. Not in the Vega Valley, in copper. So there's another couple over here. It's like a dome that's kind of like got a hole in it, and it's got spikes all over it. I don't know if you can see that, if it's clear enough. There's a number of them, and they're caught in crevices. So I can't rule out that they are not some sort of pollen, or that they are some sort of spores from mushrooms. But this is definitely something, and actually, when you look at it online, this kind of does look like some sort of rust structure. So unfortunately, that may be what that is. Now, given the fact that this technology produces oxygen and so on, could it be because of that? I don't know. But rust has a huge volume compared to iron. And anyway, I can't rule out that that is not rust. And I can't immediately rule out that these structures are not pollen, or they are not spores. But I will show you, I've already showed you how Matsumoto observed some things similar to that. And I showed you here, here, and here. And there's other examples in the book. Okay. So, you know, you could think that this was a pollen grain. You could think that maybe this was a pollen grain if you didn't know that this was a lead ball when you analyze it. Okay. And so it's important to observe what these things are. Now, given the fact that the technology tends to produce a lot of carbon, then you would expect to see carbon in there. But, you know, we'll have a look at that in a second. Okay. So, I then only have one other SEM here and a close-up on this, or a slightly different view of it. But what I'm seeing here is a form of kind of disruption going on, where we've got all these bubbles with hollow areas to them, and these cracked areas. Now, these cracked areas, I did a little bit of research on, and I'm going to go and show that in a minute. Okay? But down here, it looks absolutely bizarre. It has what looks like a boneyard. It's like skulls and bones. But we know we've got hollow structures, but we've also got these tubular structures. So I couldn't immediately find rust that had this kind of structure. And so when I go to spend more time with the sample, I'm going to be trying to understand what's going on with these structures more. But yes, it is tubes and hollow kind of like structures. So what is that? What is that? Do people know? I go over here. Got these structures down here. And there's it looks like these crystal grains have been eaten out. You know, this is almost hexagonal. And it's been replaced with something that looks a lot like carbon. And when you read these images, it tends to be that the lighter things are a heavy element. So this could be iron. And that this could be a lighter element if it's darker. So possibly carbon or silicon and oxygen, carbon and oxygen. But there seems to be a lot of this, and it's forming these crust. Yeah. So a lot more time needs to be spent. Now, unfortunately, this microscope doesn't have 16-bit. It captures in 16-bit, but it doesn't give you the ability to save in 16-bit. So you get the exposure level you take at the time. Now, one other image, but it's more of the same thing, really. So I just want to look at the paper that I found that might give us some interesting things to think about with respect to this. And that's if I can find it here. And it is in Nature Scientific Reports. And I have it here in, and I'll share the link to this, but it's uncovering the superior corrosion resistance of iron made via ancient Indian iron making practice. Well, isn't that a thing? And when they look at these samples, they see something that looks remarkably like what we've just seen on our SEM. So if we go back to that, here, these cracked plates here, looks quite like, not in this point, but these cracked plates, they look remarkably similar. I wouldn't say the same, I would say similar. Okay, maybe. So this is corroded ancient iron from India, and I recommend you read this. In here it says FESM images a morphology of corrosion product film formed on the surface of iron made through ancient Indian metallurgical methods. Flake formation in the film. And it says at the surface areas with a thicker surface film, less cracks occurred. Flake formation is noticed in studies that fine flakes are characteristic for atmospheric corrosion processes. So fine flakes are characteristic for atmospheric corrosion processes, whereas coarse flakes resemble marine corrosion, which is clearly evident in figure 1b. So 1b is this one. This is supposedly marine corrosion. So could there be some, based on where this stored, could there be some marine corrosion that is causing these kind of flakes? I'm not sure it looks exactly the same, but you know, that's what we have to go with. And they go in closer and closer and look at different things. They see, you know, some spots of silicon, okay, because you know you will have silicon when you're making iron. And this is a crude method, but the iron that John had was not crudely made, it was expertly made. But anyway, and then they've got some corrosion layers in here. So I recommend you go and study this paper, but I don't see in here the kind of structures that we've observed in the SEM images, where we are seeing these kind of like skull and bone structures down here. And for me, that's, I would like you to get out your best investigating skills and see if you can find iron that has these kind of skull and bones on them. These cylindrical sections. Okay, maybe it's just another form of rust. I don't know. Okay, so we'll look at the SEMs now. So for those of you that got that far, thank you for being with us. Okay. And I'll go back to here. So when we look at these papers, you will see that we looked at this area. Unfortunately, we missed the skull and bones area down here. But I think possibly this area is a similar kind of makeup as what is occurring down here. And then we looked at these zones in this particular image here, which if I zoom in, you can see I looked at the kind of flat smooth area, this kind of charging area. So when something's charging, it's normally non-conductive. So this might be glass, actually, silicon dioxide. I looked at this very dark area and this mid-grey area here. Okay. And then the last one was I looked at one of these two of these structures that may be organic, and then the edge of this structure here to find out what they were. Before I go on, I just want to show you what we found on one of the Vega Valley samples. So because that might give some context to what I'm showing here. So in this sample from the Vega Valley, sorry, no, this is not the Vega Valley, rather. This is from the copper that was in a Vega experiment by Henk. I noticed two things. Now, I don't believe this was effectively freshly made, taken out of the reactor and sent to me. And it has lots of circular structures on there. It also has these fibers which you see in Matsumoto's work, but I believe that these are zinc oxide fibers. And if you go and look at zinc oxide, it looks a bit like this. And this is good because this is highly piezoelectric and thermoelectric. But anyway, there's one structure here which stood out here. And it is near perfect sphere with this section off and a section off in the same kind of orientation as we saw with the Matsumoto images, which you can go and look at in his book. And then there's another one over here, which is a little bit more clear. And it has the hole here, and here it has a dimple. And so they're again at this angle, but it has a hole on one side and a dimple. And I saw this same kind of thing occur with the very first microwave ball lightning experiment that I did in the Nova reactor, where you had a hole and on the other side or one side you had a lot of carbon. So I would expect you would look inside here and it would be carbon. And so you have these spherical structures, and I believe probably that a lot of these spherical structures were these structures, but then they got laid down and then other things get deposited on them. So they kind of lose their identity in the mix. But this, as the reactor died, this might have been one of these structures similar to what Matsumoto observed. And that might be something like the structures that we observe in the shell images here, which I showed you earlier. Right, so we're going to go and look now at the analysis. And this is the Hutchison billet, which I'm now calling the Hutchison step sample for my reference. Okay, so we have the lava image, and we have, which is, go back and see that. The lava image is this one. When I can show the image, that would be good. Oh dear. Where are you? Lava image. This is what I'm calling the lava image. So we have 4 analysis and some 4 spots. We have the shell image, which looks like this. And we have 3 analysis and 3 spots. And then we have the bubbles here, and we have 1 map of the bubbles area. So we will have a look at that now. So on the lava sample, this is the area, and the first spot is on the really smooth area. And what do we see? We see that by atomic concentration, it is 77.7% iron and 88.789% by weight concentration. But by atomic concentration, the silicon content of this bulk area here is 17.416% silicon. I think the XRF data of George Hathaway was valid. Also, we see carbon here, and aluminium was just requested to be in the sample. So there was basically no carbon whatsoever, no aluminium whatsoever. So we're having a small amount of carbon in there in this area here, a really rather large amount of silicon, and iron here. Okay. Now, before I go on, I just want to refer to one piece data point, and this was by Mahadevan Srinivasan, and it was presented at ICCF 21, I think, in Japan. Is that right? Yeah, 21, I think, or 22. 21. It was in 21 in Japan, in Sendai, and it was a something that he held on to for nearly 20 years, or more than 20 years, because he was worried about reputation trap. And it was about a 3-phase arc furnace in India. Sorry, there's an advert in the background there. It was a 3-phase arc furnace, and it was making ferrosilicon iron. So this is actually an alloy which has a lot of silicon and iron in. So I'm going to look at that now. So I'm going to play, this is just a short video, and I thought this was so important at the time because this was like, he led the Babur Atomic Research Center into the initial replication attempts of Martin Fleischmann. And, you know, he held on to this data for fear of his reputation. But listen to what he says here. So, to just clarify, it's a 3-phase, multi-megawatt carbon arc furnace. So you've got carbon graphite electrodes here. You're feeding in charcoal, and you're feeding in sand, basically. And then you're feeding in scrap iron. And out of this, you will get some ferrosilicon alloy out of it. And obviously carbon you would expect to grab the oxygen or whatever, and you end up with this CO2, and you end up with silicon and iron left at the end of the day. But actually what happened is fascinating.
Made in exact quantities and put it there, and this is a continuous round-the-clock furnace which goes on for weeks together.
Right, so this is a 24-hour process which runs for weeks. Once you've started it, you have to keep it running, otherwise it all gets clogged up. So they keep it running, and so he goes on.
And at the bottom, he draws out ferrosilicon metal. Now, the observation of relevance to us is that during a 11-week-long non-stop run in 1995, he had, you're feeding silicon, 33 tons of silicon. Now, we're not talking about the production per day. 33 tons of silicon fed in the form of silicon dioxide, which contains 15 tons of silicon, 5 tons of iron, and one would expect 20 tons of ferrosilicon alloy of 75% silicon. But the actual production of the alloy was 24 tons daily, round the clock for a period of 11 weeks. And there was, every day he was producing 4 tons of excess metals, literally out of thin air. Basically, I should say carbon and oxygen. So he was very puzzled. He knew nothing about cold fusion or anything. And eventually, after talking to various people.
So to cut a long story short, they're putting in their raw materials, and they know how much silicon is in the raw silicon dioxide, and they know how much scrap iron they put in. So they should only get maximally 20 tons of ferrosilicon 75% alloy out. And do you know what they got? They got 24 tons. They got an excess of 4 tons of metal produced, with an excess of 3 tons of silicon and an excess of 1 ton of iron. That is transmutation on an unimaginable scale. But as I showed you at the beginning of this presentation, if you take carbon, which there's abundance in there from the electrodes, and carbon from the charcoal, and you take oxygen, which is coming from the scrap iron, but mostly from the silicon dioxide, carbon plus oxygen will synthesize silicon, and it will further go on to, in a ball lightning scenario, produce iron. But there isn't a massive hole in southern India. This didn't blow up part of the subcontinent, because you're talking about producing, through low energy nuclear reaction processes, 4 tons of metal through nuclear fusion per day for 11 weeks. For 11 weeks, producing 4 tons of excess metal from the fusion of oxygen and carbon. If that doesn't get you interested, I don't know what will. But that is what occurred in that instance. And so the fact that we are seeing in this data potentially a large production of silicon in this metal, which I will test, because I can see the other side of this sample. I will be able to test on this sample here, whether on this area under here, and I'll try and get permission from the owner to polish this. I will be able to test whether this is a high silicon metal. But I don't expect that George Hathaway was wrong in that, and this is what we're seeing. We're seeing a high proportion of silicon here. Okay. So that is that first area, the first spot, and there is the spectrum out of it. And the second spot was in the light grey area here, you see, in the light grey area. And this, to me, looks a little bit like potentially the rust area, but anyway, we'll see what's there. Okay, so in this area, we get synthesis, we get actually a lot less atomic concentration of iron, but we're getting oxygen here. So this is, looks like FeO2, close to. We don't see any hydrogen, so whatever. And we're getting some chlorine in here, very little silicon, and a small proportion of carbon. So that is what this area here is. Maybe this is some form of corrosion. But it is interesting that you have iron silicon here, and maybe that's why it doesn't corrode, because it has this high proportion of silicon in it. Here, it's rusting, and then we've got these other two areas. So let's see what those two areas are. So no one has ever looked at this sample in 40 years with SEM. And no one has ever shared deep microscopy of this. So it's a real honor to have this opportunity. Okay, so in this area here, wow, look at this. 77.52% of the atoms in this area here, in this dark area here, is carbon. 16.1% is oxygen. What did Matsumoto say in his book? When you collapse material, what you get produced is predominantly carbon, oxygen, and iron. Well, it started with iron, but carbon and oxygen. So there's virtually no silicon and there's zero iron. There's no iron whatsoever in this. This, to me, possibly would be the result of totally collapsed material. And so the fact that this was very brittle, it could mean that the observations of Yul Brown and Matsumoto and ourselves in other systems is supported by this, that it's actually formed carbon. Okay? So no iron at all. Right? And the last area here, what have we got there? Well, again, it's carbon and oxygen. But interestingly, it's charging. Now, if it's carbon and it's charging, how is that even possible? Like, okay, so maybe it's some form of carbon that is non-conductive. That's possible. And that is meaning it's charged. It's got some oxygen there. And again, practically no iron. So this area here looks like it's the result, potentially, of potentially contamination. But it looks like it's blending. When I see these things that are kind of blending and flowing into the overall material, I question whether it is some contamination and whether it's actually, you know, it is what it is. It is some material that was synthesized. Now, you know, if you didn't know that these ball lightning technologies tend to produce carbon and oxygen, then you might say that this is contamination. But we know that they do. And so possibly this is why this fell apart. Okay? It barely blips on the horizon, the iron. It's just carbon and oxygen. Same up here. This one has a little bit of silicon in it. So it's carbon, oxygen, and silicon. No iron at all. Pure iron is more corrosion resistant than regular steel. Also, there is an alloy of iron named wrought iron, yes, which has very low carbon content, and that makes it more resistant to corrosion. All good information. Yeah, so basically we want to understand what this material is and the raw material, because this was cut off that long thing that you see various people handle on the videos that I showed earlier. So what you missed here is that, if you weren't looking at my shot here, is that the first area here, this light grey area, this is for Corky. Just a quick review for Corky. Thank you for joining us. This is almost all iron and silicon, and George Hathaway in 1993 reported their analysis of this sample using XRF, which is not SEM, with EDS, using X-ray fluorescence in the 1980s, I believe it was, that he saw a high proportion of silicon where it wasn't present in the material elsewhere, so in these flakes and stuff. And so we are supporting that in terms of our analysis here. And I talked about the fact that it has been shown that carbon and oxygen can fuse to silicon, and that goes on to make more iron if you push it hard again. And that was in the work of presented by Srinivas, that was held back for 20 years through reputation fear. bless him, he's passed on. So, but he was a leader in the field for many years. He actually ran one of the ICCF conferences. Then this area looks more like rust because it's got oxygen and iron in there, and so this could account for the reddening of it. But it's this area here, which is black, which actually has 0 iron in it at all, and it's mostly carbon and oxygen, and this area, which is on top of this area, so it's like kind of in the center of this whole area here, and this is charging, which means it's non-conductive. Okay, and in fact it charged a bit more when we were doing this. So you've got this blended stuff that blends into these filaments. If we actually go to the image of this, what is it? This is lava. I called it lava, didn't I? This one here. What I'm referring to is this area here. You can see that this charged. So this is mostly carbon and so on. This has 0 iron in it. This has a little bit of iron in it, but you know, it's almost like that. This has the dome and it has the spike coming down. Maybe this is one of these monopole structures, and this is just what it did around it. But you have all these fibers. So anyway, that's that sample. So that is that area, and so we have silicon and potentially synthesis of carbon and oxygen. Now we go to the shell area here, and I look at these things which I suggest might be some sort of spore or pollen. And when we look at them, they have carbon, nitrogen, oxygen, a little bit of phosphorus, a little bit of sulfur. Okay. Now, all of those things I would expect to see, possibly, in something that's organic. Okay? But these are all elements that are produced by Lena. So I'm in two minds. But typically, organic material doesn't include silicon, and it can include iron. Okay? So the jury's still out on these things. A lot more work, I think, needs to be done to establish whether that's just contamination of some spores or otherwise. I looked again at another sample. Have I got both samples there? Oh, no, I took another spot on one down here. Yeah, I took another spot on another one here. And this had aluminium in it. And I'm not so sure that many organic material has a lot of aluminium in it. So the aluminium and silicon shouldn't be there. And if this dropped on the surface and is just holding there, I don't know. I'm not convinced either way that this is either organic or it's something to do with the process. I don't think we need to have this to believe that this was done with a monopole-like system. And I'm not showing you, am I? I'm very sorry. So what I missed here was... Okay. I'm looking at the shell here. I'm looking at these things that I suspected were organic by looking at them. And they have carbon, nitrogen, oxygen, phosphorus and sulfur and iron. And all of those things you can get in organic materials, not so much the silicon. And on the second sample of one of these things, it has some amount of aluminium and some amount of silicon as well. So if it didn't have either of these, I mean, these are very low amounts. So it could just be contamination on them or some reflection. But I can't rule out that it isn't part of the process, and I can't rule out that it's not an organic thing. The other thing that we looked at was the shell of this structure, which looks a bit like some sort of rust. And when we look at that, we see actually that it is 24% atomic concentration carbon, 49% oxygen, and iron is 26%. So given the fact that it has so much oxygen and so much iron, it probably could be rust, but it's the carbon content that's interesting. And also it has aluminium and silicon, which is not too far removed from the aluminium and silicon of the adjacent structures here. So is that contamination that fell on both, and and it's consistent across the two? I don't know. But anyway, I think this is the lesser interesting data than what is going on in here, which I believe supports what was said by George Hathaway in his XRF analysis, and the observations of Yul Brown in the 1980s and the observations of Matsumoto in the 1990s on the synthesis of carbon and oxygen. Of course, oxygen is the next alpha conjugate nuclei. You get 12 alphas, 3 alphas makes your carbon, and add another alpha and you get oxygen. So that's why you get a lot of oxygen synthesized. And then carbon and oxygen together form silicon. So it's not surprising that you have so much silicon and oxygen in the Earth's crust. Okay, so this is the map of a different area which we looked at. And in here, it's in this particular area, we don't see so much silicon, but it is there. We see iron, oxygen, and carbon. So the carbon is by far the most abundant element. So these plates here, wherever they are, if it didn't skip up to the top of the document here, these plates that we see here, oh dear, it's done it again. It's got a mind of its own. Oh. Come on. I'm going to use the zoom down here rather than... Okay, all right. Oh dear. It's just odd. Just odd. Okay. This is this area that we're looking at. And there's the sampling area. Okay, so not so much iron, but it is carbon and oxygen. So I believe that, you know, the interesting thing about this is you might think, oh, it's just carbon and oxygen. They're not very interesting elements. Okay, but you're starting with iron mostly. What did you expect? This system can take any nuclei, and through the process of electronuclear collapse, it regenerates elements, and it starts by producing abundant hydrogen. You're not going to see that. Carbon and oxygen, and through the elements in the periodic table. And if you look at, let's go and see what was reportedly produced by Solin in his experiments. What did Solin see? What did Solin see in here? And bearing in mind that he preferred to use was it molybdenum? Zirconium. Okay. What did Solin see? A superconducting nuclear condensate is magnetic liquid metal nuclear fuel that generates energy with the generation of coherent radiation under conditions of nuclear phase transformations in the mass of the initial product and the combination of electromagnetic, gravitational, and nuclear interactions in it. Synthesis of elements from helium, which will go away, to iron, and other heavy elements. In particular, carbon. Nitrogen, oxygen. Nitrogen is a gas, will go away. Oxygen, potassium, calcium, sodium, aluminium, magnesium, silicon, and iron. This is what was observed when Solin exposed a sample of molybdenum or tungsten to an electron beam. And in it, he says that the electron beam causes electron bunching. That leads to the creation or formation of superconducting superfluid nuclear substance and the nucleation of magnetically charged particles. Okay? So he's observing the same element synthesis, in particular carbon, and we've got silicon and iron down here, oxygen and so forth, and aluminium. Okay? So I don't think, and he's starting with, in that case, zirconium, so he's not necessarily going to end up with the same outputs as we are observing in the experiment here. So, in conclusion, I would say that this sample, even with this initial analysis, supports both the previous analysis of it, and in the context of the subsequent work by Solin, published in his patent in 1992, and by Matsumoto, published in this book, which you can now get from remoteview.icu in 2000 and now made available. That electronuclear collapse caused by coherent electrons and their interaction leads to the production of what we observe on here, which is principally carbon, oxygen, and iron, which is already part of the start, and silicon. And so I think that's it. That really is a real Hutchison sample with a Hutchison effect. We've seen the yin yang, the peak and the trough in the live analysis, which I'd not seen before on here. I saw it with you guys. We've done a little bit of characterization of that. We talked about other things that I've spoken about in the past, about how this causes the material to break apart, the formation of the magnetic monopole-like structures, the fact that they can aggregate, the fact that other authors have seen this, and this leads in aluminium to things moving around and jiggling and jellification, and in the case of something like iron, because it is actually ferromagnetic and these are magnetic things, they build and they build and they build until they just get the yield strength of whatever it is, and it tears, and it tends to tear sideways. And I think that's probably why you are seeing this stepped pattern. And also this particular shape here, we might be able to revisit this when we look at something else that I looked at on the SEM on Tuesday in a different video in the coming week. But I have found something on that particular sample from actually the Vega Valley, which blew my mind. And I think we're really uncovering the way the universe works from the lowest levels all the way through the upper levels. And I have to thank the person that allowed me access to this sample. There are other people in different countries that have also offered their samples for analysis, and this will form the basis of Mr. Possible. The book that it's going to be part biography and part analysis of samples, and that will be black and white in a reader book, and then there will be a separate book which is a color photo book which will accompany the black and white book, so that you can have extremely high fidelity images of Hutchison samples and the color maps of the analysis and so forth. So that will be Mr. Possible. And now that I've concluded this, my next book will actually not be that, because I still can't travel to the US, but I'm still doing work that will feed into that. The next book will be the book on the Vega Valley, which again will be along this lines. It will have a photo book, and it will have the analysis that goes alongside it. And I think by sharing this sample and having the courage to share this sample, which I can't imagine this was easy for John to give away. I can't imagine it was cheap for the person that had it. And you know, it's after all of these years to actually have some idea of what's going on the surface, and just the surprise for me of actually physically seeing under the live session today the same ring spots, these hexagonal structures with these spots or dimples in the middle, exactly the same things that we saw on the aluminium sample here, the fracture sample that we looked at in a number of years ago, that was produced in 2007. So this could have been produced as early as 1981, and this was 2007. But yet we see the exact same structures. And let me see if I can pull up the things of what I'm talking about on that sample there. Maybe I have it here. Maybe I don't. Did I have it in this one? I don't know. Right. Let me see. Give me a second. I'll see if I can find what I'm talking about so you know what I'm talking about. Do I have it in this one? I don't know whether I do. I do have this though. So this is the George Ohsawa cycle, carbon arc in air reaction tree. So when you are doing carbon arc in air, and we talked about a carbon arc furnace producing 4 tons of excess metal, 3 tons of excess silicon, which is fusion of carbon and oxygen. Here's the fusion, carbon there, and oxygen goes to silicon. Okay. But you can also do fusion of carbon and nitrogen, goes to aluminium. And then if you've got 2 aluminiums, you go to iron. Okay. And also Sundaresan and John Bokros used carbon arc underwater, and they proposed this process to produce iron from carbon and oxygen. And this was from 1994. And the work of George Ohsawa was in the 1980s, I think, and even in the 70s. But this is what you see coming out of an overreactor. So there we go. What we are seeing is not unexpected in a ball lightning system. It's not unexpected in a ball lightning system. So I will do one little last attempt to see if I can find this. Otherwise, I'll call it a night. Right, do anyone have any questions? Daniel Foss, I'm currently looking towards tensor annihilation as nuclear collapses as anti-gravity accumulation. Easy for you to say. Inca Steps, I like it, I like it. Any chance that organism or organic matter created in the process? Well, actually, it's funny you should say that, because actually in Matsumoto's book, he observed things that look like organic structures being synthesized. And he comments that they look like protobacteria. I'm trying to find the SEMs that he has that in. So you can go and see this in the book. Let's see if I can find it for you now. Can't guarantee I will, but so many images of things synthesizing carbon. Okay, so trust me, he has these images of a couple of things that look like they are organic. And you can't blame him. You have Leclerc that looked at his ultrasonic work and started to believe, and I believe rightly, that the things that were causing the transmutation in his systems were also responsible for DNA structure and possibly for starting life. And Matsumoto, when he's looking at these things, you start to recognize the fundamental structures of living things, and all living structures at all orders of magnitude. And so it's an inevitability that if you study this for long enough, you will start to realize that is what it is. And so when you see things that look like a bacteria, you think, well, maybe this is how it started. And so there's 2 authors that kind of went down that road of realization, and I'm now in agreement. So I can't find it for the minute. German dudes have John Hutchison kit and are firing it up. Well, that would be fantastic. He's talking about bions maybe. Has anyone tried recently to okay. With the Nova experiments, we are, and with the Ultra experiments, and with the Vega experiments, and with the HHO experiments, we are doing aspects of what John did. And essentially, in my view, you are creating coherent matter. This coherent matter forms a superfluid, superconducting condensate, as suggested by Solin in 1992. Bearing in mind that at that point they'd never shown a Bose-Einstein condensate, actually. It was still a theory at that point. But he was observing something that could only be explained by something that was actually that material. And it emits coherent radiation for a start. And so that coherent radiation must have single energy photons. And so you would kind of get that by the inverse beta decay process described by Dr. Alexander Parkhomov. Because when you do normal beta decay, you get a spread spectrum of energies of the beta particle. But when you do inverse beta decay, it comes out at one energy. That is monochromatic. That leads to monochromatic radiation. Okay? So you get monochromatic radiation coming out. Monochromatic radiation can lead to coherent radiation. Okay? So you have these solitons that then cluster together, and they form these ball lightning structures, that can then self-collapse. And so in each of these different technologies, coming at it from different angles, you are leading to a stillness and the removal of angular momentum, such that you can produce a coherent state of matter. And the coherent state of matter, when driven resonantly, leads to the collapse of matter and the regeneration of matter at a distance. And that is, in my view, what caused this material to fall apart and go into crumbly stuff, which is different elements. Any chance? Okay, Solin provided a big boost here. Yes, it did. Yes, absolutely. Floor forward, stay flawsome. Yes. I like that phrase. It's great, Corky. Yeah, it's like one man's rubbish is another man's treasure. You can paint that same analogy to art. I'm not saying your work is rubbish by any means, though, Corky. Okay, sorry, Nick, about that. I will share these images, of course. So what did anyone think they missed? I don't know if you saw anything you missed. Okay, some great comments, guys. Right. I would like to have shown this image. Maybe I know where I can find it quickly. I know where I can find it quickly. Here. Maybe. Yes, ta-da. So, here. This is one of the first couple of times that I saw these kind of repeating structures. These peaks and troughs. And it is in the fracture sample. And so you have these hexagonal structures with the spot in the center. And sometimes they have the raised bit. So you've got a raised bit here. And you have a raised one here. And you have a dimple here. So this is the yin-yang And this is on the quartz on the jewel. So you've got the same structures here. They've got a hole here and a raised bit here. And they kind of like, they trying to form some sort of regular array, but it is a bit of a mess. But you've got to imagine these things, they're their own being. And there's like a male and a female version, a yin and a yang, a positive and a negative charge. And they arrange themselves, but it's imperfect. When you've got a lot of people in a room, then you don't always get a perfect arrangement. But these are using the same microscope, the Narugo microscope, and at different scales. The interesting thing is here, the center of these structures, sometimes you get these crystals. And the crystals are quartz, I understand. And so, you know, is this synthesized or is this, I don't know, casting sand? I don't know. I had speculations about what it might be, but, you know, there's so many ways to dismiss things. And then you see it on a pure piece of fused quartz at the same scale. And so, you know, seeing those things today on that sample was really rather special for me. I don't know whether we can actually, can we get that? I can maybe show those for Corky. If I can load up the thing. It was in a live session, but I did actually take some images during the live session, so maybe I can grab those. And it's in the microscope. Where is the microscope here? There we go. And we've got a couple of images here. Not perfect. Where is it? There. So, ooh. Okay. I'm going to share this for Corky because he missed it. You are worthy. Don't talk yourself down. Right, let's see if I can actually show this. They're going to let me show you. I'm going to go here and I'm going to turn on the microscope. Is it going to show me the microscope? There we go. So you can see there's a dimple here and a hexagon around it, and there's a hexagon around this raised bit here. And if I turn those off, not the best example. We've got another bunch here. That's showing the, I'll clear all measurements. There was a range of hexagonal structures, some with dimples in and some with peaks. So you've got a dimple here in the hexagonal structure and you've got a peak here. Got a bunch of them here. Okay. So this is just an initial look-see. But these things were all observed by Matsumoto as well. You've got a nice hexagonal structure here with a dimple. Sorry, the peak in the top, and this one's got, looks like it has the dimple there. But anyway, there's a nice one here with the dimple in the middle. Okay, so definitely this was done with a ball lightning-like technology. And this is the first time that I saw it on two different technologies. There we go. All right, so I think that's probably it for me today. If no one's got any quick questions they want to ask or particular things they want me to discuss, I'll give you a minute or two. But if not, then I shall call it a night. It's 1:30 in the morning for me here. Teacher's pet. Okay, so this was a look at the Steps Hutchison sample here, and I was delighted to find the dimples and the raised sections on this, the hexagonal structures with the dimples and the raised sections, as we saw many moons ago on the 2007 fracture sample and on the 2017 lion sample by a different author. This is effectively replicating the process that was observed by Solin and Matsumoto in the 1990s, but obviously this sample being created in the 1981 to 1983 period, working with Alex Pizarro and George Hathaway. This predates that, and if this sample was looked at with a microscope by Ken Shoulders, who did handle this sample, then he will have seen, I would imagine, these structures, and that would have given him a lot of inspiration to understand what was going on in this technology. So I feel deeply honored that I have access to this part of this sample, which so many people that I have been very interested in their work and their process of discovery have handled this sample and taken samples from this sample, and to share it live with you with the first microscopy images and the first scanning electron microscopy images, in the case of the microscopy images live, to see that this is almost certainly a piece of material that was exposed to a ball lightning related technology, then it's just been a deep honor. So I can't mention his name, but thank you to the individual that has shared this sample. He has some other very important samples for us to look at. In those cases, they might not ever be able to be put under an SEM without taking a sample from them, and he doesn't want them damaged, and I respect that. But for me, thank you, and thank you, John, for allowing this sample to be independently reviewed multiple times over its history. If you hadn't done that, maybe George would not have believed things, maybe Ken Shoulders would not have believed things, maybe people in Germany would not have believed things. So you kind of like, if you create a baby but you don't necessarily understand how it works, then you kind of have to put it out into the world and let more minds active and put their own understanding and thoughts into it. And I hope that maybe when people see this data and so on, they can reflect on what's going on and understand themselves, and maybe get even more clarity in how this process works. But with that, I will say thank you very much. So Corky saying defined ORM, that's orbitally rearranged metal or something or whatever. It's a change in the electron structure of a element. Almost, I think they are related. And well, yes. So Hal Puthoff, who worked with John Hutchison via Ken Shoulders, who he kind of got on board. Hal Puthoff looked at what David Hudson was doing and said that, it was related, and I talked about that in a presentation I made in Asti in Italy, I think 2016, I think in June the 6th, 2016. So you can go and see my comments on the writings of David Hudson with the relationship with Hal Puthoff then. And yes, I've actually hosted a Ukrainian who speaks fluent English recently, and he's going to meet me on Tuesday, and we are going to translate a series. I've been given permission to do this. He speaks fluent Russian as well, and we're going to translate a series of documents by Shishkin, which Alexander Shishkin has given me permission to translate, and you will see some concepts related to dark matter and relic neutrinos and the way matter works, according to his viewpoint. But I'm quite on board with it, and I think you'll be pleasantly surprised. It will answer another huge question that I guess many people have in their lives about the true nature of how things work. And so I'm really excited about that. And so that will be coming out over the next several weeks. But that's great. And also, Chistolinov gave a presentation which I'll publish in the next few days at the recent Russian meeting, and he's talking about potentially that strange radiation and so on is related to dark matter. And that whole presentation, it's quite lengthy, so I will let it sit with YouTube and translate the English. And I have the presentation in Russian, so I will translate that also into English. But we now have a number of different authors understanding, and I think he's added some mathematical details to it. But I'm more on the physical and phenomenological and what you can see with your own eyes and you can witness repeatedly across different systems. Those are the things that I like to connect with, that are visceral, that you can gather just using your eyes and understand with just your eyes. That's where I'm coming from. But there are other people working in different ways to understand this, and so I think we're getting close to a much deeper understanding of how everything works on every scale. So yeah, there'll be a lot about that in the coming weeks. I believe the Hutchison fields are transmuting matter into an Orm state. Cognitosan, quite possibly, some of the material will do that. If you have single atoms, the idea is that they like in the platinum group or gold or whatever, that they, particularly gold because of its nature of its reactivity, it can form a state where it is superconducting, and these, as was shown by Bogdanovich et al., they had structures moving around and emitting light. Well, it's not so much emitting light as condensing matter and emitting light that then, in my view, causes the stimulation of light production from the surrounding gas. But anyway, whatever. They saw these things persisting for 2 days. Then someone said they saw them persisting for a couple of months. And then the team, Zatelepin and Baranov, said that these things can persist in metals, and they've observed it for 1.8 years. Lion re-energized some of his crust after 9 months. And Ken Shoulder said these things stay in metals indefinitely, and I think what you're going to understand from the work of Shishkin, that these what we are doing is we are getting into the inherent structure of matter and deconstructing it, and what you're seeing is a condensation of what is actually part of other matter. And so you'll see this in some of the work of Shishkin, and so the idea that it's reorganizing matter, and it is a different phase of matter. These itonic clusters, these ball lightning, it's a different phase of matter. It is a macro quantum object that can be synthesized. And so, yeah, it's totally fascinating. It's just like, this is the most interesting thing I can think of doing in this universe. Okay, so I'm going to say goodnight. Thanks for everyone's time here tonight. Sorry about the glitches in some of the equipment here, but these live sessions, I wanted to respect the person that gave this sample for me to look at, and he's been waiting since last summer for me to be able to find some way of looking at it under an SEM. now I've had a chance to do that, I'm really inspired to take more time to look at it. I think most of what it's revealed is in what we've seen today, in that it looks like it's gone through electronuclear collapse. It looks like it has the signatures of this ball lightning. It looks like that the claims that were made about it in the past are valid, and that we have seen this in other systems now, which are effectively proxy sideways replications of John Hutchison. But John Hutchison is effectively the epitome of someone that discovers things just out of curiosity and because they wanted to explore why someone was doing something and so interested in doing it and expanding it. Like his passion for Nikola Tesla not led him to just talk about it. He went to meticulously rebuild from the original source documents the Tesla disruptive discharge generator, and that was critical for him to create the effects. And a discharge generator will create these mushroom type monopole like structures, and then they can be guided, we know, by electromagnetic and fields and magnetic fields, and they like to find themselves in metals. And so when you understand what is going on, you understand that what he was doing in with our understanding now would have created these things, and that they do live in metals, and then once they're in there they can be remotely actioned to do other things and to be driven to aggregate and perform the things that we've seen happen. So what happened, right? And there is a reason for it, and so we're getting to the point of understanding what the reason is, the mechanism for it, but the amount of technologies this is going to realize is it just totally boggles the mind. It just all kinds of directions, but technologies that have been dismissed because people didn't have a ready realization of how it could even be possible. Therefore, it must not be possible, but it is happening, and so the barrier of is it possible is removed. We now know it's possible. Now what we're going to do with it. And for me, the first point of call is fixing Fukushima. We are dealing with a wall of regulation which prevents discovery of the capability of these technologies. But I believe, if you've been following my videos this last week, something which I collected in 2017 based on concepts I had in 2013, I believe we can use that with HHO, and I've been talking to Slobodan, and I think we're going to be able to demonstrate the remediation that way without having to ask anyone's permission. And that is where I would like to focus my attention with application of this technology. John told me I lost interest in the effect because it just seemed to mess things up and disrupt things, and it's like I couldn't really see any use for it. When I realized that it's not just messing things up on a structural level, it's messing things up on a nuclear and subnuclear level, but then the products are things that are not radioactive, then how can we use it? The obvious thing is to remediate radiation. And that is where John and I really connected. The passion for using this family of technologies to remediate radiation. And given the fact that we need more energy, and there's a vast quantities of thorium in the world, and actually quite a lot of uranium, and there's a lot of other elements that this technology can manipulate into potentially providing energy, then why we have a lot of good reasons to understand this more and make deliverable technologies from it. So with that, I'm going to say thank you very much for your time, and I'll see you in the next video. Cheers for now. Buenas noches, dobro noc.